Yes, of course.
So, welcome everyone to our keynote speaker, Professor Gheith Abandah, and he is Distinguished Academy with PhD and MSE from University of Michigan and his Get Bachelor from University of Jordan. He served as a full professor of computer engineering at University of Jordan, and he was the first president of Aqaba University of Technology. He is also the general coordinator of Erasmus Plus, the SARE project focusing on AI and robotic curriculum, with over 14 years experience in academia and industry. Professor Rice excellence in teaching, research, particularly in AI, uh, NLP, focus in Arabic language, machine learning. He is like offer like 67 publication, offer 1,200 citation with high index of over 21. He extensive industry experience and have a lot of experience and project development. He was successfully lead technical team in various role and project, including design, engineering, project manager, development manager, VP, developing, and general manager. Also active IEEE senior member, Professor Reis, he co-founder of IEEE Jordan section and chair it for 3 term. He always lead the IEEE region 8 community for diversity, equity, and inclusion, and establish the accept and JIT uh, JET conference, showing case his commitment to service and invitation. We encourage to everyone to join this daily lecture, and I appreciate Professor Rice for his effort to present this knowledge and experience, especially in AI and natural language processing and the application related to this area. Thank you, Professor Rice, for accepting our invitation as keynote speaker. Floor for you, Professor Rice.
Thank you. I'm going to try to share my screen now. Okay. Okay. Thank you, Dr. Shadi Saleh, for your introduction, and you for hosting me. In fact, I am, as you said, I'm a professor of computer engineering from the University of Jordan, but now I'm spending my sabbatical leave in American University of Sharjah as visiting professor. This talk, as you know, is about large language models, architectures, and applications. I'd like to start it with this quote from Andronik, who said, "The future of artificial intelligence is here, and it's more powerful than we ever imagined." I also want to recall two information. Today, the largest language models contain hundreds of billions of parameters. These are more than the synapses in a small mammalian brain. Also, these large language models are trained on large data sets equivalent to reading all the books in the Library of Congress multiple times. This talk or presentation is organized in 6 parts. I'm going to start with a general introduction about large AI models, then the architectures of large language models, then how we train them and how they generate text. Then I'll go over the main trends in large language models, some applications, and I'll end by a conclusion. Now let's review AI models. And to do this, I'm going to review neural networks, the size of a neural network, how large are deep networks, and I will share you some sizes of today's large models. Neural networks are made of layers. There are always input layer for the inputs for the data, and you get the results on the output layer. And sometimes you may have hidden layers. And there are nodes, and each node has inputs from the previous layer and an output. And usually the input are multiplied by some weights, and usually there is a constant called a bias. Now, what's the size of a neural network? The size depends on how the size is an indication of its complexity. The size, in fact, is the number of parameters, the number of weights, and the number of biases for all nodes. And this is an example for this particular neural network. There is hidden layer of two neurons. Each neuron has two weights and one bias. This is 6, and there is an output layer of one neuron, again 2 weights and 1 bias. This 3 with a total of 9. So this is a simple neural network of 9 parameters, but because of the let me go back to, because of this function can be a nonlinear function. Therefore, such a simple network can solve many linear and nonlinear problems. So it's simple, but it is still powerful. Deep neural networks are larger. Deep neural networks are multi-layer neural networks with more 2 or more hidden layers. This is the input, this is the output, and here we have 3 hidden layers. Therefore, this is deep neural network. Usually, because they are large, because they have many parameters, they need huge data in order to train them, in order to find the parameters, the weights and biases. We need many examples. We train them on huge data. But deep neural networks are powerful. They can solve complex problems, and they can provide end-to-end solutions. Like here, you can present the raw input, maybe a waveform of an audio or pixels of an image, and you get the final result at the output. Now, what are the sizes of deep networks? This varies significantly. Deep neural networks can be millions or even billions of parameters. And I'm going to give 4 examples. This is a general example, the ImageNet classification problem. And from my own research, examples of Arabic text diacriticization, Arabic poem classification and diacriticization, and Arabic spelling mistakes correction. The ImageNet classification is in fact in a famous competition. There is a data set of 1.2 million images that contain 1,000 classes like person, dog, chair, and this is large scale visual recognition challenge. Most of these images are for training, and there are subset for testing. And people for more than 15 years tried to solve this challenge, and this shows the progress from 2010 to 2017, and it shows that the top 5 error rate is decreasing. With time, deep learning is becoming more and more accurate. And now I'm concentrating on the year 2015. The winner was ResNet 152. This model achieved an error rate of 5%, and this is better than the human level, which is higher at 5%. And this model, the size of this model is about 60 million parameters. So with 60 million parameters, a special type of deep neural networks, convolutional neural networks, is able to recognize many objects, to identify many objects in large data set of images, and be it humans. Of course, with time, the error is still decreasing and the accuracy is still improving. Now, this is from my own research. I started to use deep learning about 10 years ago, and this is a famous problem for the Arabic language. We need usually people write Arabic text without diacritics, without short vowels, and there is ambiguity. Usually there is ambiguity, and because sometimes a certain word can mean more than one meaning. Like this is kataba, wrote student letter. The student wrote a letter, and this word can be wrote or box. But when you add diacritics, you can pronounce it correctly, and you can know the exact meaning of the text. So I started to solve this problem using special type of neural networks, the bidirectional long short-term memory neural networks, and of course we got excellent results. We used multiple layers, deep neural networks of 5 bidirectional LST, 4 bidirectional LSTM hidden networks, the hidden layers. This graph tells us about the general trend. When you use larger and larger data sets, the number of sequences used to train the neural network, the diacritization error decreases. And here, with this large 400,000 sequences or sentences, the network is able to diacritize Arabic text very accurately. And this is the size of this network is about 5 million parameters. So with 5 million parameters, you can capture most of the Arabic language grammar and morphology and enable and diacritize text correctly. Now jumping to 2023, we used for the same problem these large language models. We used ByteT5, which is pre-trained byte to byte. I'm going to come back to it later. And this is a much larger model. And of course, with better models, we achieve lower diacritization error. Here, it was 1.45, and with a larger model, the error drops to less than 1%. This is also a problem. I'm interested in Arabic poetry and processing it and doing things like classification and diacritization. This is one verse, one famous Arabic poetry verse. وأمطرت لؤلؤا من نرجس وسقت وردا وعضت على العناب بالبرد. Classification is classifying it, finding the meter or the pattern of the poem, because there are multiple meters. For the classical Arabic poetry, there are 16, and this is the basit meter. Also, it is very important to diacritize Arabic poetry, because in order to be able to write it and enjoy it, you need it to be diacritized. Here, we also used bidirectional LSTM network. This is a deep model, but the classification problem is not hard, but the diacritizing Arabic poetry is harder, because the structure of the poetry is more difficult than normal Arabic text. And also, we have smaller data sets to train such a model. So we used transfer learning. We trained the classification model on large poetry data set, and but the diacritics was trained on on a subset of Arabic poetry that is properly diacritized. The classification accuracy approaches 100% when you have multiple verses of one poem, but the diacritization error is not that perfect. It is 3.5%, and we're still working on this problem in order to improvement. But look here, with this model is about 7 million parameters. With 7 million parameters, you can capture the music in the language, in the text for poems, and find the classes, and also do a good job in diacritizing it. So this means with such a model can learn the Arabic language and the Arabic poetry, and is able to solve such a difficult problem. This is the fourth and final example, which is Arabic spelling mistakes correction. There are common spelling mistakes, and of course we need to correct them, and we use transformers. Transformers are very famous. I'm going to come back to them. The base model for the transformer is 65 million, but with a scaled down transformer model of about 2 million, we were able to correct with an accuracy of 98.9 correction accuracy of these common mistakes. Now, what are the sizes of large models these days? Models, okay, what are large models? We can say that large models are models that cannot be trained on common computers, because large models changes with time. Something that was large 20 years ago, it is not large anymore, because our computers are more capable. So when the model is larger than what a common computer can handle, then this is a large model. And these large models nowadays are in billions or even trillions of parameters. This table give you some examples. OpenAI DALL-E that generates images from textual description is 12 billion parameters. Google Lambda chatbot 137. The OpenAI GPT-3 used in ChatGPT-3 is 175. Recently, this year, Meta released Llama 3. It is much larger, 405 billions. Nowadays, the OpenAI ChatGPT uses ChatGPT-4, which is this is not official, but most people think that it is 1.8 trillion parameters. There are even larger models, not for language, but for recommender systems. Facebook Xeon EX is 12 trillion parameters. This is the introduction. I'm going now to move to the architectures of large language models. And I'm going to start with the dense networks and move to recurrent neural networks. This is taking things from the historical sequence. People started to solve problems related to languages using dense networks, then recurrent neural networks, and more recently, transformers and pre-trained language models. This is, again, a dense network. Dense networks can be used to handle text. Dense, they are called, of course, dense because every neuron is connected. Every neuron in any layer is connected to all the neurons in the previous layer, dense connections. They can be used to process text. The input here is going to be the letters or the words of the sequence, and maybe you want some to solve some classification problem or like that. They are suitable for simple and moderate tasks, but these are not efficient for complex tasks. They're not efficient for handling text and sequences, because they don't learn things related to the order of the tokens or tokens at the input. For 30 years now, recurrent neural networks, about 30 years ago, recurrent neural networks were introduced, and they are there are special type of neural networks where the neuron output affects its subsequent input. So there is a feedback from the output to the input, and this feedback is used in the next step. So, and these now are called memory cells. Here you can present a sequence like words of a sentence. You present the first word, then the outputs of the neurons are used as inputs to themselves in the next step, and so on. So at the end of the sequence, you're going to have an output that not only depend on the current input, but also on the previous tokens of the sequence. Recurrent neurons are used, as I said, to handle time series data or text sequences. They are very powerful, and I used them 10 years ago to solve complex problems related to the Arabic language, and they performed excellently. But they are slow because the sequence is presented one token at a time. There are better solutions nowadays, which are mainly the transformers. The transformers are a huge revolution in natural language processing. In 2017, Google researchers led by Vaswani introduced the transformer, a new architecture at that time, and they call it transformer. They don't use recurrent neural networks. They just use attention mechanism. And this is from the 2017 paper. This is the basic architecture of transformers. Here, there are encoder modules. This is one module, but this module can be repeated in times. And here is the decoder modules. This is one decoder module, but there can be multiple modules stacked one on top of the other. The final encoder module outputs, the final encoder module, the outputs are fed to the decoder modules. These can be used to do text translation. Like you can enter text in the Arabic language and get it in German language. But of course, you need to train it to learn how to translate from one language to another. I'm now going to concentrate on the encoder. Input words. Words are usually input in parallel. Input words are you input a vector of tokens representing your text. And there are embedding that transform these tokens into their respective meanings. This layer is trainable layer. It is trained to translate tokens of words into their meanings, long vectors of that describe each word. Then after that, there is an addition of the positional encoding. Word positions are added to the embedding vectors. Now, yes, you input the text at one time, but in order to not to lose the sequence, we add to these vectors encoding of their positions. So here we get vectors that describe the meaning of the tokens and their positions. And now, because the text is presented not serially, it's presented in parallel, the computations that the transformer do is not sequential, but can be done in parallel. And when you have some parallel hardware like a GPU or TPU, then you can do the required computations in parallel and much faster than the recurrent neural networks. Then there is the multi-head attention. The multi-head attention updates each word representation by attending to paying attention to all other words in the same sentence. So, and again, there are multiple layers of such modules, and the word representations keep changing from and the meaning of a word is changed in order to take into consideration the surrounding words and the context. At the end, we get powerful representation of what are the input and what's the meaning of the input. Now to the decoder. The decoder is similar, but here there is multi-head attention. This is okay. When you train it, when you train it, you need to give it the input and so that it trains to give you the correct output, but also you give it a hint of what's the for every token, what's the next token. So there is also for the outputs, we need embedding and adding the positional encoding, and there is also attention, but here there is cross attention, not self attention. When you try to generate the output, you need to give attention when you are trying to generate an output in like in German language. You need to attend to the proper words in the other language, for example, in the Arabic language. This transformer can be trained efficiently because the computations can be run in parallel, and the transformer can be scaled up, can be made larger and larger, more and more parameters, and you get more and more powerful language model. We can grow transformers through increasing the number of layers. Deeper networks can capture more complex patterns, enlarging the model width, the embedding vector width. higher dimensionality embedding vectors allow for richer representations and multiplying the attention hits. Here it's showing that there are 3 attention hits, but usually it is much more. More attention hits enable the model to focus on multiple aspects of the input simultaneously. Okay, so if there is any question, I welcome any question, or if you want to me to elaborate in anything, it's okay to do it anytime during my talk. But open your mic and interrupt me if you wish. Now let me move to pre-trained language models. There are now training a large language model is expensive. So you don't want to train a language model for every language task, natural language processing task. So now, for efficiency reasons, we have now pre-trained language models, such as BERT, T5, GPT-3, and 4. These are all transformer-based and trained on vast amounts of text. They are pre-trained, they learn language models. Some of them are multilingual. They are trained on multilingual datasets and can learn multiple languages. Now, once you have a pre-trained language model, you can use it for multiple tasks. After pre-training, they can be fine-tuned on specific tasks, such as democratization or question answering. And I'm going to give you more examples on this. So you start with a large corpus like Wikipedia. You train a large language model and you get a language model. Then you need smaller task-specific dataset like question answering. You fine-tune the language model and you get your final model and use it for prediction. This is a good time to move to training and text generation. I see that there is a question from Dietrich. What are the main differences between pre-training and fine-tuning large language models? Okay, yes, this is pre-training. Okay, usually we start with transformers that are not trained. The parameters are random numbers, random small numbers. They don't do any useful thing. With large corpus, we do pre-training. We do the initial training. We train them so that they learn the language model. And after that, we get a transformer with trained parameters suitable for that knows the language, but it cannot do anything. Cannot do interesting things or cannot solve our tasks like sentiment analysis. In order for this pre-trained model to be able to do sentiment analysis, we need to fine-tune it on another data set that has, for example, samples of text and the classes or the sentiments. With fine-tuning, you modify the language model into a specific model that is able to solve a specific task. Now, how does fine-tuning enhance large language models for domain-specific? You must use it, because without fine-tuning, the language model only knows the language and cannot do interesting things like sentiment analysis. Now let's talk about large language model training. This is Detrick is related to your question. Large language models are pre-trained on huge data sets using something called self-supervised pre-training. You get good text from multiple sources, and you modify it. You can predict the next token, like the student went to, and ask the model to complete it. The student went to the school. So you ask the model to predict the next token. This is called self-supervised, or predict masked tokens. And this is an example. Here, President Franklin, this is masked, was born masked in January 1882. So the model is trained to find the masked tokens. And this was used in Google's T5 language model. And through this type of pre-training, the model is able to capture information and learn the language from many examples. Then we do fine-tuning, fine-tuned on various language tasks like text classification, entailment, similarity, question answering, and this is for question answering. This is a question: when was Franklin D. Roosevelt born? And there should be some data set that connects this question with this answer, and with this fine-tuning, the large language model becomes able to answer questions. Of course, before that, it has learned many things, and with fine-tuning, with the smaller data set, it learns how to answer the questions. And this is very powerful method and very successful method. And we used it for things like diacritization and correcting spelling mistakes. Now, let's talk about how much data we need to train models. In general, the training data points is increasing exponentially. This is from 1950 to the 2020s. But the rate of training data set increase is now increasing in a larger rate. Of course, this is log scale, this is exponential. and the knee is after 2006 when Jeffrey Hinton and his colleagues show us how to train deep neural networks. So this is like the era of deep learning. But we're using more and more data, larger and larger data sets to train large models. This is from this year, Llama 3. It was trained on 15 trillion tokens. This is exponential increase, but also the available data is exponentially increasing, but on a slower data rate. And there is a threat that after 2028, we will not find more data to train our largest models. There is a question: what are the advantages and limitations of transfer learning in training large language models using huge data sets? Of course, when we do transfer learning, we don't use huge data sets. Huge data sets are used in pre-training, and we use smaller data sets in transfer learning. Transfer learning, when you have a model trained on something and you train it to do it differently. What are the advantages and limitations of transfer learning? Advantages are obvious. With a small data set, you can get powerful model that was originally trained on a larger data set. So with a smaller training effort, you can reach a powerful model. What limitations? Limitations of transfer learning, of course, depend on, you need some data. You need enough data. The large models you're fine-tuning have billions of parameters, so you need also a powerful machine in order to do pre-training, fine-tuning. Now let's talk about generating text. These models, the large language models available now do text generation, like ChatGPT. In general, the large language model output generation is often deterministic. Given a certain input, they're going to give you the most probable output. This is a problem because deterministic outputs may lead to repetitive and predictable sequences. The solution is to add some randomness. Randomness can be introduced to diversify output and improve creativity. In fact, there is a parameter for this. The temperature parameter is used to control the level of randomness in output generation. With low temperature, the model is going to have some small randomness and produces more confident predictions. But with higher temperature, we increase the randomness, allows lower probability tokens to have a higher chance of being selected. Maybe you don't get very very coherent results, but in many cases, you're going to get innovative outputs. I'm going to tell you before that there is another question. What role does temperature, what role does temperature play in controlling the creativity of, I'm going to state it again. With temperature, you can control the creativity. When the temperature is low, the output is highly similar to the text that it has trained on. But with higher temperature, there is more creativity, there is more randomness. The outputs are with higher and higher similarity, the output is less and less similar to the text or input or data set that it has trained on. Another question, how can large language models avoid generating repetitive or redundant text? Maybe let me use this slide in order to give you more about how an example chatbot is trained. This is Llama 2 from Meta. But this is chat Llama 2. This year, Llama 3 was introduced, but this is still helpful slide. The target of the Llama 2 creators was to have a chatbot like ChatGPT that is helpful and safe. Give us good answers, and safe does not give us bad things. The training was done in this way. The first step is pre-training on large unlabeled text corpus. This is self-supervised training, and with large pre-training data, you get language model, Llama 2. Then this is the language model, but it's not useful. You need to do fine-tuning so that you get something useful. And the stage 2 was supervised fine-tuning in order to convert it into a chatbot. And in order to do that, there is supervised fine-tuning using a special data set where it learns for certain questions what's the proper answer. There are examples: question, answer, how to interact, logs of real chats. But this is small, and the available data sets are small and not enough to get accurate and comprehensive chatbots. So after supervised training, they move on to reinforcement learning with RLHF, reinforcement learning with human feedback. Now, reinforcement learning is that the model generates some outputs and gets feedback about the or maybe punishment or reward according to how the chatbot results, the model results are good or bad. This can be done using some metrics automatically, but sometimes with human intervention. With human intervention or human feedback, some outputs are inspected by humans, and they give like yes or no, good or bad. They give feedback to the training process, so that the training process with time avoids bad outputs, and because of the rewards, uh, uh, keep giving better and better results. So with this three-stage technique, large companies like Google, OpenAI, and Meta are developing large chatbots that can we can use them in general problems. Now let's move to an interesting thing, which is model trends. With time, the AI models and large language models are changing. And I'm going to concentrate on these four model trends. There are, as you know, with time, there are larger model sizes, but there is continuous research in model architectures and designing better and better architectures. Now we know that these models the text models are going multimodal, and we're moving from narrow to general AI. Let's start with large model sizes. The model size is increasing exponentially. And this is from the 1950s to the current time. This is the log scale of the number of parameters. And here we have more than 10 trillion parameters. So this is higher than exponential growth. Let's concentrate on the multiple types of AI models. The green are vision models like ImageNet. And with time, from 1950 to 2022, the model sizes increased by an order of 10 million times. But for the language models, the Magneta, the squares, have increased much larger. For the same period, it is 100 billion times the number of parameters has included. There is a question, how can large language models assist in research and academic writing? I'm going to come back at the end about applications of LLMs. Now, I'm concentrating here on the large model sizes for language models. And there are two trends. Before 2018, the improvement was 0.1 order of magnitudes per year. But after the creation of or the introduction of transformers, the language model size is increasing at a higher rate. about 0.9 orders of magnitude per year. And the main reason is related to the transformer model. The transformer is very, very efficient. We can, and parallelizable. You can have very large models and you train them on huge data sets. This will take a lot of computations, but we can distribute the computation on hundreds and thousands of processing elements. Okay, this increase also, the model size increase is directly related to computation complexity. The computation complexity is also increasing exponentially. This is the pre-deep learning era, and this is from 2006. This is the deep learning era, but here even higher, which is the large scale era that has started after the introduction of the transformers. This means that training the large models is becoming more and more expensive. This is also a log scale of the cost in US dollar, the training cost, and now there are large language models that cost multiple millions to train them. For example, Llama 2, training Llama 2 cost $5 million US. Companies like OpenAI and Google and even Meta for Llama 3, they do not disclose the cost of training their models, but there are some estimates that developing a new large language model cost in about $100 million. This is a limitation. We cannot grow these language models much further because the cost of training them is huge. Okay, there is a question. What strategies can be employed to enhance the energy efficiency of large language model architecture, as these models are huge and large model sizes and training using huge data? One strategy is to use better hardware and specialized hardware, specialized computation accelerators like GPUs and TPUs, and there is a huge innovation in these areas. The other technique is by continuing to do research and designing better model architectures. And I'm going to share with you this graph. This is very interesting. EfficientNet is a model that is used for computer vision. It's not related to language models, but from the paper of EfficientNet 2021, I'm getting this interesting chart. Now here the number of parameters, and on ImageNet image classification problem, you see that with larger models, you get better accuracy. But also with better models, better architectures, EfficientNet introduced better architectures, better algorithms, and with the same model size, like 40, we get higher accuracy. So there is now great research on developing models that are more efficient, that can learn from smaller data set, or that can learn better. Now, another trend, as you know, is going multimodal. Multimodal are models that can process and generate multiple modalities: text, image, audio, and these are becoming more prevalent. An important trend is the AI is moving from narrow to general AI. Narrow AI is an AI who can solve a certain task, but cannot solve other tasks. General AI is AI that can solve general multiple tasks. And this is the famous singularity graph. We know that human intelligence is increasing due to health, education, slowly, but AI is increasing much faster. And there is this singularity point where when the AI is going to be smarter than humans. Let's talk more about when and how we're going to reach the singularity. AI will achieve human level intelligence this decade. Ray Kurzweil in 1999 predicted that AI will achieve this level in 2029. People did not believe him at that time. Most experts thought that we can reach it in something like 2010. With time, they expect to reach it in 2042, and this is 3 years ago. And 2 years ago, AI experts think that we are going to achieve it in 2030, which is close to Ray Kurzweil prediction. And there are people like Elon Musk think that we are going to reach it even sooner. These are examples of AI surpassing human intelligence in certain tasks, not general, like defeating world chess champion 1997, winning Jeopardy 2011, mastering Go 2016, achieving superhuman performance in video games 2010s, generating realistic text and images 2020s. And there are more examples. Tumor diagnosis, designing a computer chip, cracking math puzzles, winning bridge card game, and protein designing. Of course, you know about OpenAI ChatGPT. It is also some type of, it has some general capabilities, not as humans, but it can generate human-like text. OpenDEL E2 version 2 generates images from natural language descriptions. And for me, DeepMind Ghetto is very interesting because it is a generalist agent, one AI model that can solve 600 tasks. And it can act as it can control a robot, it can do image recognition, classification, captioning, and it can do things related to natural language processing. There is a question, can large language models be used in data quality monitoring of data sets, like completing missing values or detecting duplicates by using their... Yes, of course, yes, of course. But again, you need data set to train it to do what you want. This is I think this is a question that all of us think about it. Let's compare the human intelligence versus the artificial intelligence. Which is better? Now I'm going to show you this table. Human at this side and artificial intelligence at this side. And now I'm going to give you the what we know about the human brain and the best artificial intelligence models. The estimate is that we have about 86 billion neurons, but the interconnections between them are much more complex, 60 trillion connections, but they operate in a relatively small speed, from 0.5 to 100 meters per second. Neuron signals travel electrically and chemically with this slow speed. Our memory, we can have trillions of chunks of data. But for the artificial intelligence, there are not that many neurons, like 10, this is in the order of 10, 100,000. But the number of parameters corresponding to the connections is 1.8 trillion. Still much. This is ChatGPT 4. The speed at which computers work is close to the speed of light, much faster, and the memory is unlimited with the cloud storage. In about 5 years from now, the human intelligence is going to almost stay the same specs, but we're going to have models. The prediction is that we're going to have models with hundreds of trillions of connections, much larger than the synapses connections in a human brain. And if we extrapolate the computational power to 2049, AI is going to be 1 billion times smarter or more powerful than humans. I'm going now to talk a little bit about applications. Shadi, remind me about the time.
Yeah, we have time free for you as we can. We
Okay,
are familiar to go quickly by applications in conclusion, and it's nice. There are many interactive questions in between.
okay. I'm going to try to end as fast as possible because I see that it's 1 hour and 20 minutes. So let me go faster now. Applications of large language models, of course, for natural language processing, like text generation, text summarization, machine translation, sentiment analysis, question answering, and chatbots. They are also used for code generation, code completion, code debugging, code generation from natural language descriptions, content creation, article writing, script writing, creative writing, customer service. We can have chatbots for customer service or for virtual assistants. Education, there are applications in education, personalized tutoring, language learning, educational content generation, and of course in scientific research, examples in drug discovery, material science, climate modeling. We're doing this project, developing applications to correct Jordanian spoken Arabic to proper language using machine learning techniques. This is a funded project by the Jordanian Scientific Research and Innovation Support Fund. We have a large team that includes technical people and from the Arabic language. The idea is that in Jordan, there is the Jordanian dialect. And this is not acceptable in formal settings. So we need to translate it to formal Arabic, proper Arabic. And we use two models trained on large data sets, training data sets, one to do translation and one to do diacritization. In order to do that, these models are pre-trained models, and we fine-tune them on this problem. In order to fine-tune them on this problem, we've collected a data set of two parts, Jordanian dialect data set and modern standard Arabic with mistakes. And most of the effort was to translate these samples into proper Arabic, error-free. This is the source of this of the Joda sample. But the great thing, we've used a pre-trained transformer from the T5 family. We used the I'm going to skip this. We used particularly the BY-T5, and we selected this variant because it accepts byte input and it is tolerant to mistakes in the input. And the great thing is that once the dataset was ready, we are able to translate Jordanian text to MSA. This is like language translation, translating local dialect to another the proper Arabic. And the result was great. I'm going fast because I want to finish before 8 my time, which is maybe 5 your time. So going to conclusions, AI, as you have seen, AI models are getting larger and smarter very fast. But smarter AI has great disruptive effects, and you know about the disruptions of general smart AI. So I'd like to end with these two questions. How can we acquire the necessary skills and knowledge to adapt to the rapidly evolving AI landscape and leverage emerging opportunities? And what strategies can we employ to mitigate the potential negative impacts of AI while maximizing the benefits? Thank you, and I'm ready for any question.
Thank you, Professor Gheith, for nice and pleasant information and presentation. I am very, to be honest, happy with this interactive question as well. There are many questions which is like not normal, so it's like looking is very interested presentation. Maybe we have short time. Maybe can you please switch your microphone or camera, or we can type your question directly in chat. Maybe I guess there are two questions from Susie. How did a large language model handle context and ambiguity in language? And there are also one question from Nadia about what's the difference between Arabic and other language in context of large language models.
So, Suze, you mentioned this question. How do LLMs handle context and ambiguity in language? About context, okay. They can handle context when you present them the whole context, not just the current question, but the previous questions and answers. Now, when we are interacting with ChatGPT, whenever we give a prompt, ChatGPT considers the previous prompts. About ambiguity, it learns with time the intent. So sometimes you're not clear, and but because it learns statistically, it can sometimes even without clear question, it can know or predict your intent and answer according to the intent. So of course, this is not perfect because sometimes you give it a clear answer and you get not good answer. And the second question from Nadia, what are the differences between Arabic and other languages in the context of large language models? There are differences between, let's take something like T5, T5 large language models. They are trained on tens of languages, including Arabic, English, German, and they learn the differences between the different languages because they are very, very powerful. And not that what they learn in one language, they are able to, the knowledge that they learn from one language, they can use it to answer questions in another language. Of course, the Arabic language has a lot of similarities and differences with other languages, and this is beyond the time we have here. Are there any other questions?
So I guess we are reached that time. So I appreciate your presentation. Maybe we have